change in our DNA. We said that DNA is information, right? And it's the order of the nucleotides that determines that information. And so it's kind of like spelling, right? We can say a mutation is kind of like two S's in misspelling. Is it one? I feel like maybe two. Ironically, I'm not sure how to spell misspelling, but misspelling, okay, is a change in the order of the letters of a word, and that changes the meaning, right? So, for instance, if the word is Mr. Kramer, and I jostle these up, right? If I put both M's in my name at the beginning, and then I put the C, and then I put both R's, and then the E, the R, and the A, right? Two S's. Okay, two S's for misspelling. Thank you, Brandon. MMCRRERA, right? The information is lost, right? You see this and you think nothing, right? You see Mr. Kramer and you think awesome teacher, right? But the idea is that's the order of those letters that matter, okay? And so mutations, oh, look, I even had it right here. Boy, that is an oversight on my part. Mutations are misspelled words, okay? So think about the order of the nucleotides as a word, and if we misspell those words, then it changes the meaning, usually in a way that prevents us from understanding the information, right? That's the idea. It's rare that you misspell something and you get a new word that's actually better than the initial word, right? Can you imagine if that were the case? You just go in and you never let spell check fix your mistakes because it always makes them better, right? No, that's not how it usually works, right? Okay, let's start here by thinking a little bit about the causes of mutations. We talked about this with our superheroes, right? In real life, mutations happen all the time. The most common way that mutations occur they are mistakes during DNA replication. Let's say this is of the two types. It is very rare that these mutations will occur during DNA replication, but this is the most common source of mutations. Okay, it's still pretty rare, right, that you would have mutations in our DNA. Remember, we talked about how accurate it is. The DNA unzips. You want to take it down? Yeah. How the DNA unzips, right, and how that allows it to be very, very accurate. Every time you get a new DNA molecule, it's half original and half new. So it's pretty accurate. And mutations are very rare, but of the sources of mutations, mistakes during DNA replication are the most common. As our cells divide and as we grow over time, right, these mutations will start to develop. And so it's thought that that's what causes us to age, and that's why maybe diseases are more common in older people than they are in younger people, right, because they've lived a longer time. They've had more mutations accumulate in their bodies, leading to the conditions of what we associate with age. Mutations can also be from the environment. So if there's something that's high energy, Brandon was talking about the flash and how he got his mutations from a particle accelerator. Particle accelerators are something that physicists use to do nuclear reactions, and they're super high energy machines. And so the people that work with them have to be really careful, right? They can't come into the same room as the particle accelerator when the experiment's going on.
Well, there was one man who went in there when it went off.
Okay.
And it also spread all over the city, created a bunch of other people, just like except other powers.
Right, it was bad, right? For most people, it would be bad. Now, the second thing that can cause it is exposure to chemicals. And most of the chemicals that we associate with mutations are called carcinogens. Carcinogens are chemicals that cause cancer, but the way that they cause cancer is by first causing mutations that cause cancer. So let's maybe jot down carcinogens cause mutations that cause cancer. And the state of California is really good at labeling chemicals that have been associated with cancer. So it's not uncommon to see, on something you bought, maybe a cleaning product or something like that, it'll say on the label, the state of California recognizes this chemical as carcinogenic, right? Now, that doesn't mean that the state of Pennsylvania doesn't. It just means that in California, they have to label these products because of the way they govern themselves. Go ahead, Owen. Well, that's a good question. I certainly hope not. The question is all of our food carcinogenic? I certainly hope not. But there are, people that are concerned that when we over-process our food, when we make our food able to last for long periods of time on the shelf, that's good for business. That's good for having products that you can sell. But is that good for our health, right? And I think that there are products that are questionable. Like, for instance, BHT, which is a chemical that's found in Cinnamon Toast Crunch, my favorite cereal. BHT is supposed to be pretty bad for you. So you can look these things up. You can Google these, because we have the internet. You can Google these things and find all kinds of information about them. Yeah. Yeah, I'm not sure about that. I'm not saying that they are or they aren't, but that's something that you should look into. I think it is good as a consumer and as a person that cares about your health and development to look at what you're eating. And there is all kinds of food chemistry and food analysis about what we eat. So yeah, I will say I think food is important, and that food is eating healthfully is not just eating a diversified diet, it's also making sure that you're aware of what you're eating and the impact it can have on your body. So two sources of mutations. One just happens when our cells divide, and the other happens because we're exposed to either high energy sources or chemicals like carcinogens. Any questions here? Okay, let's start to think a little bit about the impact of these mutations. This little flowchart here is to help us think about the process here, right? A mutation that happens, remember, in our DNA, maybe we could add the word or the letters DNA, right? A mutation that's in our DNA is going to cause us to have a new amino acid sequence. So mutated DNA is going to change the order of the amino acids. So when we go to use our code chart, maybe we're supposed to get met val ser, and we end up getting met val val. Or maybe because of the mutation, we don't get any protein at all, right? So all those are possibilities. So the mutation causes a new amino acid sequence, and because there's a new order of amino acids, you get a protein. Remember, we think of these proteins as tools. So tools with a new shape. A new shape. And you might be thinking, well, new is good, right? New is good, right? But not necessarily, right? If I have a screwdriver and it has a new shape that makes it look like a hammer, well, that's great. Now I've got something that can hammer nails, right? But what if I need a screwdriver? Well, now I have a hammer. I don't have a screwdriver, right? So there's a problem there, right? So a lot of times mutations and changes in our information are actually bad for us. And so that's the first category. We're going to underline three possibilities. When we talk about mutations, there's the bad ones, there's the neutral ones, and there's the good ones. Okay? Yeah, the good, the bad, and the ugly. So the first one, the bad, right? This is the majority of mutations that we find. When we say detected, we mean mutations that we find because the new shape doesn't do the job the cell needs it to do. So for example, maybe the mutation causes a screwdriver to become a hammer. But but we need a screwdriver, not a hammer. So the new shape doesn't do the job the cell needs it to do, and so this causes disease and death. And so when we say it's a bad mutation, it's bad because it leads to that organism not living, right? So bad is contextualized by the organism, its ecosystem, all the other organisms that it's living around, its niche, all those things can affect whether this is good, bad, or neutral. Neutral mutations, we don't know, because neutral means that it's neither good nor bad. And so these ones are undetected. We have no idea how many neutral mutations happen in a lifetime because there's no way to tell, right? We would have to sequence the genome of every cell in our body, and there's trillions of cells in our body. So that's never happened, right? We have big data and we have cheap technology, but it's not that cheap yet, right? And it would take a long time to do that. So the new shape is minor, but the protein still does its job. So if there's a mutation and it changes the protein in some way, but it still is able to function, maybe it's a screwdriver, but now it's got a longer handle, right? No big deal, right? It's still a screwdriver, okay? It's still able to do its job.
What does that thing say? What does that say?
Mutation, screwdriver to become hammer. Oh boy, maybe I should have said screwdriver becomes hammer. Sorry, becomes hammer, but we need a screwdriver. Okay, so a new change isn't good if it's not what we need. That's the idea. Okay, and then the last one.
We need a one.
Oh, sorry, what'd you say?
Oh, we need a one.
Oh, but we need a screwdriver. Okay, so if we get a hammer, that's cool. But if we need a screwdriver and not a hammer's not going to do the job of a screwdriver. And so that would be bad for that organism. The last category we can think about is good, okay? And good of the three are extremely rare, extremely rare. It allows an organism to have a trait that actually allows it to live better, okay? So it's got to be a trait. It's got to be something that changes in the body of the organism. Okay, so it can't be something that is just at the cellular level. It's something that has to affect the whole organism. Okay? And it has to allow the organism to live better. That's what makes it good, right? Is that they're living better. Okay? And this is extremely rare. There's lots of diversity in humans, right? We look very different. We have different abilities. We have different talents. Even our minds are different. We have different personalities, right? But, so there's lots of varied genes in us. There are people that believe that these varied genes are the result of mutations. Okay? And then there are other people that don't believe that. And so there's a role here for belief, okay? And what you believe and what you don't believe, is going to be affected by many different things that we're not going to be able to get into. But there are people who believe that we have all these traits and these genes because of mutations, and that these were good mutations that stuck around over time. Okay. Do you guys have any questions on that? Just want to stress that is a belief that some people hold. Okay, that's their assessment of what's happened. Okay. All right. Let's continue on just a little bit farther here. So when we talk about mutations, I like to think about words. Ooh, somebody wants to get in. Sorry. It's Megan. Hey, Megan. I'm sorry. I just saw you. Were you waiting long? Sorry about that. We're just doing the mutation notes. They're in the agenda. Okay. All right. So I like to think about a gene is like a sentence, okay? It's like a sentence that's made up of letters that we call nucleotides that are grouped together in three-letter words that we call codons. And so here's just a real simple sentence, okay? The cat ran far is a little short sentence, okay, right? We've got letters. The letters represent nucleotides. They're grouped together into little 3-letter words that are codons. And a group of codons is a sentence. So you can hopefully picture a cat running somewhere, right? And it's far away. So that communicates information. There's different ways that we can mess that up, though. Okay? And so that's what we're going to look at here. There's 3 ways that we can mess up the meaning of that sentence. The first way is called a substitution mutation. What changed in that sentence here? It was the cat ran far, but now it's the bat ran far. And so let's maybe jot down a C got switched with a B. Does that change the meaning of the sentence? Definitely does, right? This is the subject of our sentence. It went from the cat to the bat. So now, I'm picturing a bat, which normally flies, right? Now it's running and it's going far away, which we're happy about, right? Because it's a bat. But, it doesn't mean the same thing. Just that one little switch completely altered the meaning of our sentence. We call that kind of mutation a substitution. When one letter gets switched for another, it's a substitution. Let's look at the next one, okay? In the next one, do you see what we did here? This is called an insertion, which probably makes you think that we added something, right? What did we add? Yeah, we added an A. Let's jot that down. We added an A. So we got an extra A in here. I'll just label it here, okay? And so look what happens. When you add an extra letter to a DNA sentence, remember, it always groups the letters together in groups of 3. That's what a codon is. It's never 2, it's never 1, it's never 4, it's always 3. And so look what happened. We've now changed the grouping, okay? And so now the first word was supposed to be the, but now the first word is at. And the second word was supposed to be cat, but now because of the grouping, the second word is ika. Instead of ran, it's tra, and instead of far, it's ufa. Okay? Which doesn't mean anything, right? This is gibberish. Can you see how this would be bad for ourselves, right? The instructions are completely changed just because we added a letter. That's called an insertion. A deletion is just the opposite. Look what we did here. We deleted a T. So let's say we removed a T. If we take away a letter, our sentence went from the cat ran far. Now it's going to change the 3-letter grouping again. This is now called, the first word's now heck. Instead of the, it sounds like we're cursing, right? Heck. Instead of cat, it's atter. Instead of ran, it's amp. Instead of far, it's R. Pyrotop, right? You see how just one little change can totally change the meaning of the sentence. The information is lost. Any questions here? This is why mutations are typically bad, right? Typically, you don't get something that's really poetic as a result of a random change. Was that too fast? How are we doing? Good? Okay. Here we go. Last little bit here. Types of gene mutations, okay? We just looked at a couple of examples of them. There's really 2 types. The first one is a point mutation, and you can always tell it's a point mutation because it just affects the sentence at one point, right? That first one that we did, the bat ran far instead of the cat ran far, just one word got messed up. And so we still knew something was running and it was going far away, but what was running changed. So one codon gets messed up. And so this one usually happens when there's a switch. Maybe underline the word switch. A C gets switched to a B, or a C gets switched to an R. And so the cat turns into the rat, and it changes the meaning of one word, but the rest of the sentence is intact. A frame shift mutation changes the grouping. The grouping of the mutations, or the grouping of the codons, I should say, changes. So it's a frame shift mutation. Where that name comes from, you guys remember when we boxed in the codons in the last part? We were framing them, right? We were putting them in a picture frame. And now because we added a nucleotide, that picture frame got shifted to the left or to the right. And so it changed the way the letters were grouped. And there's two ways that a frame shift can happen. You can either add one or you can remove one. Add one or take one away. Either way, if you add or take one away, it's going to change the three-letter group. Any questions here, guys? Good? Yes, albinism is a mutation. And in some contexts, you could even describe it maybe as a good mutation. If we're talking about an environment that is Arctic and white, right? Maybe that would help organisms, although they probably would still struggle a lot with the sunlight. There's a lot of sunlight reflected in Arctic places from the snow. Okay, last little bit. I think there's a little summary. Let's go ahead and see if you can do this, and we'll go over the answers, okay? See if you can match the word to its definition, okay? If you're struggling, see if you can find just one or two. I know we just introduced this. There's a mutation where one kind of switch with another. It's a switch. Okay, let's back first. Substitution, right? It's like basketball, right? Substitute a player. Here, correct. You know, you gotta be careful. So I can see it. Yeah. Let's take one more minute, okay? No harm in guessing, right? This isn't for a grade or anything, just to give us some feedback on this. There's a lot of words here to keep track of. They all kind of mean the same thing, right? At the end of the day, whether it's a substitution or insertion, it's a mutation. It's a change in the DNA. Okay, guys, let's go over the answers. Whenever I do matching, I always like to start with the definition, so it's less reading. So let's start with number one. It says a mutation where one nucleotide is switched with another. What do we put for that? What do you think? Go ahead, Owen. You put what? E, as an elephant. A substitution mutation is correct. And substitution, I always think of basketball, because basketball players are always getting substituted, right? They get tired because they sprint so much. So substitution, right? You substitute one for the other. Switch them out. Number two, a type of mutation that affects one codon and one amino acid. Sam. B, point. Great job, Sam. A point mutation affects the sentence at just one word, right? So it's a point mutation, just one point. A mutation that adds an extra nucleotide. Brandon, what'd you put?
Insertion.
Insertion. You're right. Insertion. You insert an extra nucleotide that's not supposed to be there. Number 4. A mutation that removes a nucleotide. Oh. D. You got it. A deletion. If we take away a nucleotide, we're deleting it. And then lastly, Owen, a type of mutation that changes the grouping of codons. A. The frame shift mutation. So if you don't have this, go ahead and change it. No big deal. E, B, C, D, A. E, B, C, D, A. Any questions? How are we feeling? We need a quick break.